Welcome to this explainer. Today, we're diving straight into one of the most intricately engineered mechanical spaces in your entire body, the eye. Specifically, we're going to decode the fascinating and sometimes incredibly urgent mechanics behind retinal detachment. It's this wild condition where biology perfectly meets physical engineering, representing a critical structural failure in the eye's inner layers. If you've ever wondered how such a delicate, complex system actually holds itself together and what happens when it suddenly fails, well, you're in exactly the right place.
Okay, let's dive into this. I want you to imagine the inside of your eye like a beautifully wallpapered room. The wallpaper in this analogy is your neurosensory retina. That's the super delicate, multi-layered neural tissue that actually captures light and lets you see the world. It lines the inner surface of the eye and normally rests perfectly flat against the wall, which is a supportive layer called the retinal pigment epithelium, or RPE for short. A retinal detachment is pretty much exactly what it sounds like. It's as if that delicate wallpaper spontaneously just starts peeling away from the wall. And this happens either because something is mechanically pulling it off from the inside or because there's a hidden fluid leak pushing it away from behind.
To wrap our heads around how this happens and how surgeons fix it, here's our quick roadmap. First, we'll cover the types of retinal detachment. Then, we'll look at vitreo-retinal traction. And finally, we'll do an overview of the surgical repair techniques.
All right, starting off with Section 1, the types of retinal detachment. Let's look at the actual mechanisms of failure here.
Now, you'd probably assume the retina is just firmly glued down everywhere, right? Well, actually it isn't. It's really only pinned down anatomically at a few specific spots, like the optic disc and the very front edge called the ora serrata. For the whole rest of its surface area, it totally relies on a delicate balancing act of 4 mechanisms just to stay attached. We're talking interphotoreceptor cellular glue, hydrostatic fluid pressure, physical structural support from the vitreous gel inside your eye, and an active fluid pump driven by that RPE layer. When any one of these mechanisms fails, the retina is immediately at risk of peeling away.
Now, what's really interesting about this next concept is this highly intimidating medical term you'll often see, regmatogenesis. I know, it's a mouthful, but please don't let it scare you. It simply comes from the Greek word regma, which just means a break or a fissure. A regmatogenous retinal detachment is by far the most common type we see, and it all starts with a physical tear in that delicate wallpaper we just talked about.
And it literally happens in a domino effect. Step 1. As the vitreous gel inside your eye gets older, it undergoes something called syneresis. That just means it liquefies and structurally collapses. Step 2. This structural collapse creates abnormal mechanical traction, physically pulling on the retina. Step 3. That pulling force eventually exceeds the tissue's strength and boom, a tear forms. Finally, in Step 4, that liquefied vitreous fluid slips right through the newly formed tear and pulls underneath the retina. It completely overwhelms the RPE's natural pumping capacity, physically lifting the retina off the wall and starving your photoreceptors of the vital metabolic support they need to survive.
But, a tear isn't the only way a detachment happens. Let's quickly compare the 3 underlying mechanical problems. First up, we have the regmatogenous type we just discussed, which is driven by a break and a fluid leak. Then, we have tractional detachment. Now here, there is no tear at all. Instead, fibrovascular membranes, which are often caused by underlying conditions like proliferative diabetic retinopathy, grow and physically pull the retina away from the RPE, almost like shrinking scar tissue. Finally, there's the exudative type. This acts like a massive breakdown of the blood-retinal barrier. Things like severe inflammation or tumors cause fluid to just accumulate right beneath the retina, pushing it off the wall without any tear or traction happening at all.
Moving right along to Section 2, vitreo-retinal traction. We really need to understand this gel-like structure inside the eye, because this biomechanical pulling is basically the primary villain in most of these detachments.
Let's compare a healthy vitreous to an aging one. A healthy vitreous is this beautifully engineered, totally transparent gel made of water, collagen fibrils, and hyaluronic acid. It gives the retina crucial biomechanical support. But as we age, that vitreous liquefies and its structure starts to collapse. Eventually, it naturally pulls away from the retina, creating what doctors call a posterior vitreous detachment, or PVD. Now, a clean separation? Totally normal part of aging. The real trouble starts when that gel remains abnormally stuck to the retina in certain spots as it tries to pull away. Because when that aging vitreous pulls way too hard on a stubbornly attached spot, you get severe structural damage. The consequences of this abnormal adhesion are no joke. You can get horseshoe retinal tears or operculated tears, which is where a piece of the retina is pulled completely free, kind of like a plug.
You can also develop chronic vitreomacular traction or even macular holes right in the very center of your vision.
So, the absolutely crucial point to grasp here is that this isn't just some static issue. It is highly dynamic. Just the simple, everyday act of looking around your room creates dynamic fluid motion inside your eye. So if you have a partially liquefied vitreous with these focal sticky spots, every single movement of your eye creates repeated, dangerous, mechanical pulling on that weakened retinal tissue. It's literally a mechanical emergency that gets worse simply by you using your eyes.
And if the retina does detach, your body can sometimes, kind of panic and make things significantly worse through a condition called proliferative vitreoretinopathy, or PVR. You can think of PVR as basically scar tissue gone completely rogue. It's this abnormal wound healing response where RPE cells migrate into the vitreous cavity, they form these membranes on the surface of the retina, and then they begin to aggressively contract. This severe traction literally crinkles and distorts the retina. It generates massive mechanical forces that can completely ruin an otherwise successful surgical repair. Okay, on to our final section, surgical repair overview. Let's talk about the biological plumbing and construction techniques doctors use to fix this incredible biological failure.
Every single decision a surgeon makes in the operating room is dictated by 4 main engineering goals. First, they absolutely must physically reattach the retina. Second, they have to relieve that dangerous vitreo-retinal traction. Third, they need to permanently seal up any retinal breaks. And finally, they have to prevent any recurrent fluid from pooling back up again. To pull this off, surgeons have a pretty incredible biomechanical toolbox. They use retinopexy, which applies laser or freezing cryotherapy to create scars that essentially spot weld the tear shut. They might use a technique called sclerobuckling. This is where a tiny silicone band is placed around the outside of the eye to physically indent the eye wall inwards. It brilliantly changes the eye's whole geometry just to relieve those pulling forces. Then there's pneumatic retinopexy, where they inject a gas bubble to press the retina flat. And finally, the pars plana vitrectomy. This is a procedure where the surgeon actually goes right inside the eye to physically remove that problematic vitreous gel and relieve the traction entirely.
And this brilliantly illustrates another challenge: keeping the retina perfectly in place while those laser spot welds actually have time to heal. To do this, surgeons use internal tamponage agents to temporarily press the retina back against the RPE from the inside. They can use gas bubbles, which are great because they just gradually absorb into the body naturally over time. Or, for the more complex cases, they might use silicone oil. Now, oil provides a much longer-lasting press against the retina, though the catch is it typically requires a second surgery down the line to remove it.
Now, the success of all these procedures relies heavily on one major factor: time. Why does that matter so much? Because a retinal detachment is a profound medical emergency. Photoreceptor survival declines incredibly rapidly the longer the detachment lasts. Surgical success hinges on things like the duration of the detachment, whether the central macula has peeled off, the presence of that rogue scar tissue we called PVR, and the size and number of the breaks. Basically, the faster you fix the plumbing, the more of the house you save.
We've seen how anatomy, fluid dynamics, and biomechanics all interact within the eye to cause and ultimately fix this intense condition. But looking forward, the horizon is even more fascinating. As we continue to map these complex mechanics, one has to wonder, could the next generation of robotic surgical assistants, or perhaps pharmacologic vitreolysis, where we actually use drugs to safely dissolve the vitreous gel before it ever even tears the retina, be the ultimate tools to prevent retinal detachments entirely? It's an incredible intersection of biology and advanced engineering, for sure. Thank you so much for joining me for this explainer. Keep learning, and I'll see you next time.